Hello everyone, my name is Mohammed Noor Al-Awad, a researcher and a PhD student from ITMO University. Today I'll be presenting our work about optimizing LLM code suggestions using feedback-driven timing and lightweight state bounds. This work is prepared with my colleagues Sergey Ivanov and Olga Tikhanova. So as we know, LLM code assistants have become very good at what to suggest, like predicting the next line, completing functions, or even generating full modules. But the question of when to show these suggestions is still underexplored. For example, mistimed completions often interrupt the developer's flow, reduce trust, and waste GPU resources. So our work starts from this insight, like great suggestions at the wrong time are still bad suggestions. So we focus on timing, we design a bounded adaptive policy that adapts to the developer's behavior. So the goal is to show suggestions at the right moment and to improve the acceptance and keep the GPU load predictable and efficient. So our main contributions are, first, we introduce a lightweight delay controller that adapts suggestion timing based on recent acceptance rate using a logistic function for logistic mapping. Secondly, we added a state anchoring to distinguish between developers mode, for example, implementing and debugging modes. This is we used to keep suggestion responsive but not intrusive. And in real deployment, our adaptive timing raised the acceptance rates sharply and also sharply reduced the blind rejections. And we cut off inference calls per accepted suggestions by about 75%, which in its turn improved both usability and efficiency. And here we see how the system works in practice. So it starts with the VS Code plugin that logs telemetry like typing speed, edits, and command usage. So every minute, this data is summarized and sent to the state classifier, which infers whether the developer is implementing or debugging based on his activity. So the detected state and recent acceptance rate are then fed into the adaptive timing control, which computes the optimal delay within the safe bounds that we'll talk about a bit later. So after the delay finishes, a request is sent to the LLM to generate the suggestions. And then the developer response, whether it's acceptance or rejection, are then fed back into the loop, which allows to continuously adjust in real time. So overall, it's like a feedback-driven cycle that adapts minute by minute without interrupting the developer's flow. And to make our timing adaptive but still stable, we built a high-level state anchoring technique that runs once per minute, so it's pretty lightweight, and it uses the developer telemetry typing cadence, navigation, command usage, and the short code diff summary. So yeah, then these data are then fed into a prompt based LLM to infer whether the developer is implementing or debugging. Yeah, and this module is stateless, so no training is needed. And it actually reached about 84% accuracy on our manually labeled data. So this binary state anchors our delay. For example, we show suggestions a bit delayed when the developer is debugging and a bit faster when the developer is implementing to keep responsiveness. So the base delays, which are 1.1 seconds for implementing and 1.3 for debugging, were actually derived from the real inter-keystroke intervals of our developers, which links timing directly to the developer behavior. So once the developer states defines the safe delay range, the system fine-tunes the exact timing needed based on the recent acceptance behavior. So every minute we compute the acceptance rate and feed it into a scaled logistic function that adjusts the timing delay. This should happen smoothly. So we tune the parameters to make the system most responsive around the point where developers start finding the suggestions distracting. So the result scales the base delay. So it tightens when the suggestions are well received, and it relaxes when they are mostly rejected. Finally, we limit the changes to plus minus 0.1 seconds per updates, which keeps the adaptation gradual and stable. And of course, if the telemetry is missing, the system defaults to slightly longer delays for safety and predictability. So this slide shows the adaptive delay controller, which maps the developer state and recent acceptance rate into the optimal timing delay. So as shown on the left in this curve, higher acceptance leads to faster suggestions, while debugging naturally slows things down to avoid interruptions, for example. So overall, it forms a bounded feedback loop that adapts in real time, which maintains smooth and predictable system load. Yeah, and about the evaluation, we evaluated our system in 2 month real world deployment with like actual developers and researchers from our center. So all of those developers are actually like experienced with at least 3 years of experience. So they use the VS Code plugin, our VS Code plugin, voluntarily in their workflow, mainly writing in Python. So, and we use the plugin to log like minimal data such as delay values, acceptance or rejection events, decision times, and a few other IDE metrics to help in other researches. But of course, nothing sensitive or intrusive. And of course, participants gave explicit consent and they can opt out anytime. So, yeah, our deployment was organized in 3 phases, which each one at least 2 weeks. So the first phase used no delay, where suggestions appeared immediately after every keystroke. The second introduced like static delays between 0.6 and 1.4 seconds. Finally, the third phase applied our adaptive policy, combining the logistic controller with the smooth state bound. So the key metric we analyzed were the acceptance rate, showing like when the suggestions were used, and the blind rejection rate, cases where suggestions are dismissed like almost immediately within, for example, 0.3 seconds, which means like the developer didn't even read them. So these two measures let us quantify both usefulness and timing quality. And here we see the main results of our module. So when we moved from no delay to static delay, acceptance rates jumped from around 5% to above 15%, which like confirms that most rejections came from poorly timed suggestions. And by adding our adaptive controller, we pushed acceptance further, for example, to above 18.6%, which is like a relatively gain of about 20% over static baseline. At the same time, blend rejections dropped dramatically from around 8% to around like 1%, and then down to 0.36% with like the adaptive timing. So this also shows like major efficiency gains. So the number of inference calls per acceptance fell from 20 inference calls per one acceptance to 5 inference calls per one acceptance, which is like a reduction of about 75% in compute cost. And because the controller operates within bounded ranges, the GPU planning and resource allocation are like much more predictable for now. And here we show a representative session with about 27 acceptance rate. So the curve illustrates how the delay adapts smoothly over time. So it tightens after accepted suggestions, and it relaxes when there are a lot of rejections, but always like staying in the safe range for the developer state. So yeah, this smooth control removes what we call bogus sticking, where timing used to swing between like too fast or too slow, and as a result, the suggestions are noticeably calmer and gives like more natural user experience. And here is like a demo of our plugin showing how timed the suggestions are. So we basically use our tool to build our other tools. So yeah, this should give a hint of our system. So yeah, to wrap up, we point out that even a small feedback-driven controller can make a big difference, as like it improves both how the tool feels and how effectively it runs without like heavy modeling. Of course, this is just a start. We only tested in VS Code, mostly in Python, and acceptance rate isn't the same as true productivity. And for the next steps, we want to like track different outcomes, things like post-accept edits, predicting optimal suggestion links, getting LLM requests based on developers' behavior. This will help us to explore how to optimize when, how much, and what to suggest. So our long term is a fully adaptive assistant that feels natural, helpful, and like smart about its own suggestions. So yeah, that's it. Thank you all for your attention.